Computers reason when they manipulate precise facts that have been reduced in string of zeros and one and statements that can either be represented by true or false. The human brain can reason with vague assertion on claims that involve uncertainties or value judgment. The air is cool, that speed is fast, or she is young. Unlike computers, humans have common sense that enables them to reason in a world where things are partially true. Fuzzy logic is a branch of computational intelligence that enables computers to represent vague and uncertain concepts used by humans to describe our world. Fuzzy set theory is based on the concept of partial membership to the element to a set. A membership function value in a real unit interval 0 and 1 is used to describe the membership. In fact, each element belongs to the set. Could you please shut down your microphone? With a membership degree. So we have a partial truth. Okay, fuzzies are generalized traditional sets where objects can only take values in 0 and 1, so they belong or not to a set. Just to give an idea about what I meant with uncertainty, let's try to define light blue. Humans have an imprecise idea of what a color is. Different people can refer to light blue with different colors. Fuzzy logic is a mathematical model that is able to represent this uncertainty in order to make a machine able to reason with it. If we apply this theory to unsupervised learning, we get soft fuzzy clustering, where each object is assigned to different groups with a certain degree. This is represented in the figure with different shades of color. You please shut down your microphone, please. In the figure with different shades of color, we have the same points as before, but we can see that
the speaker, all others kindly mute.
This is represented in the figure with different shades of color. We have the same points as before, but we can see that they have been assigned to the two groups with different membership values. We can see red and green dots that certainly
there is some constant noise. Others kindly mute, please, other than the speaker.
You can do from if you are the administrator of the talk. Okay, so we have the same points as before, but we can see that they have been assigned to the two groups with different membership values. We can see the red and green dots that certainly belong to the green and red groups. The one on the left and right sides of the picture, and then we have orange and light green dots that represent the uncertainty. Indeed, if we consider the geometrical distance as similarity measure, the two dots in the center do not certainly belong to the one of the two groups, saying that they belong to the first and second group with a possibility of 0.5, it's more like our brain reason. So data stream Recently, there is a huge increase in amount of data that are not static, but arriving in a continuous and changing manner. It is impractical to store and use this data, in this form. Moreover, classical data mining techniques are no more suitable to deal with this kind of data, so new models are needed in order to process them. Particularly, we need to process a finite number of data at a time. We use a limited amount of memory. We need to predict, classify at any time and in a limited amount of time. And we need to take into account the evolution of data. So, after having introduced all the concepts that can be useful to understand our approach, let's start with our algorithm. It is a classification method for string data based on a semi-supervised fuzzy clustering algorithm proposed by Pedrich. It incrementally learns the model since it is applied to non-overlapping chunks of data so as to enable continuous update of clusters. Moreover, using a splitting and a mapping mechanisms, it dynamically adapts the number of clusters and classes in data. Indeed, a fixed number of clusters and/or classes may not capture the evolving nature of data. Just a brief sketch to understand how the algorithm works. Data here are divided in subsequent chunks, a subset of data containing labels, labeled and unlabeled data. As you can see, data in each chunk could have labels, such as the a priori known classes red and blue and green, but there could also be unlabeled data, the white dots. Moreover, image shows that the data distribution changes during the time, that is, the number of classes and the number of data belonging to them could change at each time t. Indeed, in the second chunk, we'd have more data belonging to the green class, and in a third chunk, a new class appeared, the blue class. Let's focus on a single step. At each time, dynamic incremental semi-supervised fuzzy CMIS is applied to the data in the chunks and it returns fuzzy clusters, that is, a membership matrix that associates each sample with each cluster with a certain degree and label prototypes that summarize data in each clusters. Clusters are then used for classification. Indeed, the label of the closest prototype is assigned to each sample. When a new chunk arrives, the process is repeated starting from the prototypes of the previous chunk. In this way, the information about the old data are injected in the new chunks. The old model could be no more suitable to describe the new data, as in this case where the green dots are increased. So a splitting mechanisms based on the reconstruction error and conditional fuzzy clustering is used to create two new prototypes and then assign them to the more similar data. In this way, the model dynamically adapts the structure to the incoming data. Now a new chunk is arrived and a new class is appeared, the blue class, thanks to a mapping mechanisms that decouples the number of a priori known classes from the number of clusters used to model the relationship in data. The algorithm is able to manage the new classes and data belonging to them. The process continues until there are available data. Indeed, the string data could be infinite. So, the first example I want to show you is about educational data analysis. I will use this case study to briefly show you the behavior of the algorithm and how it can be used to analyze and interpret data coming from the interaction between students and virtual learning platforms. Virtual learning environments are becoming very popular with the advent of internet, and these are online learning platforms where the teaching materials are collected, so distances between students and courses are reduced or completely deleted. They provide synchronous and asynchronous tools such as chat, forum, wikis to support the students, but their most relevant characteristic is that they are able to trace the student behavior, and any interaction with the platform is stored. The aim in this kind of analysis is to monitor the student's behavior during the time in order to predict its outcome. Will he succeed or will he fail an exam? This is the goal, our goal. In the study, we used a subset of the Open University Learning Analytic dataset. The Open University is one of the largest distance learning universities, providing free open data relating to the online courses. It contains demographic data together with aggregated clickstream data of students' interaction with the learning environment, collected on daily basis. In this work, we used the semesters as a temporal unit, so we train the model on the actual semester and then we test on the subsequent one. At each time, one chunk is processed and prototypes and membership matrix are returned together with the classification results. I would like to highlight that since our algorithm is based on fuzzy clustering algorithm, its results are interpretable. Each prototype summarizes the attributes of all the students' items belong to the clusters. Particularly, it is a medoid, so in this sense, it can be interpreted as a typical student profile. As an example, table 1 reports the attributes value for the two prototypes P1 and P2 that were generated by the algorithm for the first chunk. We can see that P1 is associated with the fail class and P2 with the pass class. We can observe that the two clusters share some similarities, such as low education level, or age band between 35 and 55, or no disabilities. On the contrary, differences are observed between some other attributes in the two clusters. Prototype 2, representing students that have passed the module exam, show higher interaction values with the virtual learning environments than prototype 1, representing students in class fail. This is an easily predictable result, but from this analysis we are able to extract information about the learning supports that are more related with the final outcome, pass or fail. For example, among the learning platform resources, the most relevant ones in terms of class separation are the number of on-page visualization, the number of out collaboration, the number of visited subpage, etc. These results could be used by the teachers as feedback useful to guide the course design and to support problematic students. These results could be used to extract rules able to describe the algorithm results. For example, if the number of clicks on forum are high and the number of out collaboration are high, and etc., the students will probably pass the exam. Of course, to better represent the human reasoning, these rules should be fuzzy. In this way, we can represent in precise way the concept high, low, etc. However, this is a working task and we have not still implemented the explanation feature. We have firstly analyzed data in terms of the features that describe them. Now we can analyze the students in regard to the groups that have emerged from the computation. In this example, we have 29 students and 2 clusters assigned to the original classes fail and pass. The clusters can be explored to categorize students according to their membership to the different clusters. In the figure, there is a graphical representation of the membership matrix returned by fuzzy clustering for the first chunk. Rows indicate students' item, whilst columns correspond to the two clusters. Each cell in the matrix indicates the membership degree of a student's item to a cluster. This membership degree can be interpreted as a matching degree, indicating how well each cluster prototype describes each student item. Yellow cells indicate high membership values, while blue cells indicate low membership values. Intermediate values are represented with different shadow or yellows and blue colors. It can be seen that for the most of the student items, the membership to the first and second cluster are well defined. This means that such items have a high matching degree to one of the prototypes and very low degree to the remaining one. On the contrary, for some students, for example, number 10 and number 22, we observe shaded color gradation. This means that the student items are described by both prototypes with a different certainty degree. This result could be used to group students' items according to their profile, and it can be used to support students that need help. Of course, in this example, I've shown the results coming from one single chunk. In real data analysis process, we have prototypes and membership matrices for each chunks coming during the time. So we could observe changes among students' classification during the time, together with changes in data distribution. For example, two prototypes could be no more suitable to describe the students in the chunk. So more prototypes labeled with the original classes fail and pass could emerge from the computation. In the same way, if different target class occur in a chunk, for example, withdrawn or distinct, a new prototype will be generated to describe data belonging to that class. A different domain is the digital health, where we have applied our algorithm to predict bipolar disorder episodes. This is a joint work with the Polish Academy of Science. Bipolar disorder is a chronic mental illness characterized with changing alternate episodes that range from depression, mania, mixed state, and euthymia. Based on the recurrence of these phases, pharmacological and psychological approaches are important to prevent further episodes. However, the frequency of control visit is usually insufficient to provide early intervention at the start of the episodes. And therefore, in recent years, there is an increasing interest for real-time monitoring of bipolar disorder episodes with the use of smartphones. Acoustic features that are obtained from the interaction of the patient with ad hoc application have been shown to be valid marker in detecting bipolar disorder phases. However, data collected with these devices are partially labeled, since only the medical expert can verify the actual state of the patient only on certain days. And it is easy to understand in this context that the time is an important component and it has to be taken into account. In this work, we analyzed the acoustic feature belonging to a single patient, daily collected, and we divided the data in subsequent subsets called chunks that have been analyzed through dynamic semi-supervised fuzzy means. The aim of the analysis was to predict if a change in the patient status occurred, and graphical visualization techniques were used to improve the interpretability of the results. Indeed, medical experts that have to analyze these results are not technicians, so we need to make the results easily interpretable for them. In this example, data belonging to the third chunk are shown in a two-dimensional space. We can observe from the first figure, the one on the top, the two a priori classes, disease 1 and healthy 0, and we can see that they are quite mixed on the lower part of the image, the red and the green dots. The two images below show the models returned by the algorithm with 100% labeling, the one on the left, and 25% labeling, the one on the right. These models are based on clusters. We can see on the left that 4 different clusters have been used to describe the two original classes, and particularly 3 clusters are used to describe the lower part of the figure where the original classes are mixed. When the information on data, that is, the number of labeled data, decreases, the algorithm needs more clusters to accurately describe the original data. So we can see on the right that we have more clusters, 7 clusters, that are mapped with the original classes, disease and healthy. And in this way, the accuracy is preserved. Indeed, with only 25% of labels, we obtain comparable classification results as for the case of 100% labeling. This is a quite important result for a real domain where labels are very rare. Again, we can visualize the prototypes of each chunk in order to have insights about data belonging to each cluster. Here we have 4 prototypes representing the 2 original classes. On the left, we have the acoustic features describing the data, and we can see, for example, that phone calls in cluster 0 that refer to healthy patients have high values for the feature F0, the first feature. As for the phone calls in the cluster 3 that refers to patients in disease episodes, values for loudness feature, the second one, are very low, and so on. This analysis can help physicians in their data understanding, and particularly it could help in detecting patterns useful to recognize the onset of a different state. Finally, in order to further analyze data in each cluster, we use the swarm plot, these graphs that represent data distribution by considering each single feature. Figures show data distribution of each feature for a given chunk and a given cluster. This illustration is complementary to the heat map with prototypes, the one we saw before. For example, it shows that values of feature loudness have high variance and some outliers, differently from the other features that appears to have less outliers. Moreover, it is clear that we have positive value only for the first 2 features, and both positive and negative values for the remaining features. Moreover, we can compare data distribution belonging to different clusters, like the 2 images, and to observe changes in data distribution from one cluster to another, given the same chunk. For example, here we observe different distribution for the feature loudness, the second one. Other example, just few. The algorithm could be applied to any domain where the temporal factor is relevant and data are partially labeled. Financial frauds are exponentially growing in the last decades due to the money dematerialization. Consequently, credit card is becoming an emerging problem. Fraud detection systems are used to discover and identify fraudulent activities that are already entering the system. The huge amount of information related to credit card activities make the manual analysis time-consuming and impractical. The study of customer behaviors allow automatically separate legitimate from fraudulent transactions. Due to the dynamic nature of credit card transaction data, incremental learning rather than static learning is suitable for fraud detection. In this context, the assumption of label data is quite unrealistic. On the contrary, since investigators provide a feedback on system in form of labeled transaction, partially labeled data are available. Thus, we applied our dynamic incremental algorithm to chunks representing transaction occurred in 12 hours. And the algorithm proved to be effective in correctly identifying the fraudulent transaction. And finally, the last example, another completely different domain when we have applied our algorithm is occupancy detection. It is very important in smart city application. The aim is to detect the absence of people in the room in order to switch off lights, ventilation, and all the tools that require energy. Since the presence or absence of human can be used for saving energy and safety purpose, accurate automatic occupancy detection in building has recently grown attention, focusing on assessment or smart spaces that are aware of the state and can act accordingly. Sensors are commonly used to measure the state of a room in terms of light, temperature, humidity, and CO2. Indeed, they allow to automatically infer the presence or absence of people in the room. In the data we used, each data sample was defined by 5 features: temperature, relative humidity, etc., which have been measured every minute in a room in a given period. Each sample is classified in one of the 2 possible classes: non-occupied room or occupied room. As a consequence, this dataset is structured as a stream of chronological sorted data sample, which can be processed as with data stream algorithm to verify the room conditions. Okay, so we have seen how our algorithm works. We have seen in detail 2 main applications, but we have seen that we can apply our algorithm to every kind of data that evolved during the time. Here you can find some references of my works. If you are interested, you can read them, or you can write to me by email. You can find here my my web page, and following the link on the QR code, you can find the slides of this presentation. So you will have all the references and all the material you need. So thank you for gave me this opportunity and for having listened to me. Thank you.
Thank you very much, ma'am, for sparing your time for today's webinar. It was indeed a very informative session. I request all the participants to drop their queries or doubts in the chat box.
Okay, was my audio on?
It was.
Okay. Okay, here. I'm looking to the chart. Are there any questions? Should I read the chat?
Yeah, the participants, if you have any questions, you please put it in the chat window.
Okay, I'm reading here.
Hello. Archana madam?
Yeah, I'm reading if there are some.
Yeah. Any questions, madam?
Mm,
No, sir.
Participants, if any questions, you please put it in the chat window. Kishore sir?
How bioinformatics can help in artificial intelligence? This is a nice question.
How bioinformatics can help in
Can help
AI?
in AI. Actually, I think AI, artificial intelligence, can help in bioinformatics. It's quite the contrary. Indeed, usually bioinformaticians use statistical analysis to tackle their data, and artificial intelligence could be useful to discover hidden patterns in data and a relationship that experts didn't know that there was there. So it could be very useful. Another question, what would be state-of-the-art research issues? About what? About stream data analysis? State-of-the-art research issues. Actually, there are no many stream algorithm based on fuzzy logic and semi-supervised that can be applied to semi-supervised data. So our algorithm is quite novel. Is AI required in all applications? Okay, our algorithm is
AI required for all the applications?
Yeah, our algorithm is a machine learning algorithm.
Is AI required for all applications?
Yes. Where IE plus fuzzy logic is required. So this is interesting, especially for who doesn't know fuzzy logic. Fuzzy logic is quite useful when we need to represent concepts that are vague, and it can be useful for explanation, for example. So AI plus fuzzy logic could be used for explain results given from other machine learning algorithms, or it can use for represent medical data. For example, we can represent data in with their CRISP value, such as I have 38 grades of fever, or I can say my fever is high or my fever is low. So I can represent these concepts using linguistic terms. In this kind of problems, fuzzy logic is very useful. Thank you. Thank you for good session. How can use artificial intelligence for preventing intrusion? Okay, I'm not very expert of cybersecurity, even if we applied our algorithm to credit card fraud detection. Our algorithm could be used for anomaly detection. So we use the unsupervised part of our algorithm for anomaly detection. Any sample that differ from the other samples is interpreted by the algorithm as an anomaly, and And then in this way, you can recognize intrusion or frauds or anomalies in general, anomalies in the industries, you know, in the mechanical parts that there can be some anomalies, and you can recognize them in this way. What are all software or tool you use in your work? Actually, this algorithm has been implemented in Python, and so I use Python for my work. Previously, I used MATLAB, but now Python is much more common, and many libraries are available. So it's a good choice for me. Hi, Gabriella. Thank you for your presentation. I have one question. How do you deal with frequently changing data? Can we incrementally retrain the model to adapt to the new data? Hi, Akhtar Jamil. Thanks to be here. And yes, frequently changing data. Actually, we do not retrain our model. The model is we create a new model as new data arrive. So we divide data in the different chunks, and we train our model on the current chunk. So if new data arrived and their distribution is modified, a new model will be automatically created. So we don't need to retrain the model. This is an interesting point with stream data. We don't need to save all the data that arrived during the time, because although we will not have enough space, but we can preserve historical data through prototypes. We inject our historical information in the new model through the prototypes. If you need, we can talk about that later. Thanks, madam. Thank you. What dataset you use or other dataset in your research work? Dr. Jamil, it depends. Some datasets I use, for example, the one on learning analytics, credit card fraud detection, and the occupancy detection were open data, so you can find them on the web. If you need them, just write me and I will give you the link. I forgot, actually. On the contrary, data on bipolar disorder, they are proprietary because they were collected by the Polish Academy of Science in a previous work, so I can share that kind of data. Okay, then thank you for your question. Thank you. If you need to contact me, you can, there were my email, you can write me whenever you want.
Thank you, madam. Thanks for the wonderful speech.
Thank you.
And thanks for answering all our participant queries.
No, it was a pleasure. I'm happy that they were interested in this topic.
Yeah, it was very nice.
So,
thank you very much.
Thank you. Have a nice evening.
Yeah, I think you can share the PPT.
Yes, ma'am.
PPT, yes, it's already on. It's already on SlideShare. But if you want, I can send you the PPT or the PDF as you prefer.
Sure, madam, please.
Okay, I will do that in few minutes.
Yeah, wait for a minute, madam. Bindu, madam.
Yes, sir.
Okay, we can conclude now.
Yeah, definitely. And I think Archana is there. She's going to take it up.
Okay.
Before which we can give a
Okay.
virtual memento. I think
Shall I?
Yes,
Meghna.
ma'am.
Yeah.
I'd like, yes, ma'am. So I'd like to request Dr. Archana NV, Treasurer of IEEE Mysore subsection, Professor and Head of the Department of IEEE NIIT Mysore, to give the concluding remarks about the session.
Yeah. Thank you. A pleasant evening to all the participants, resource person and the execom members. The webinar series on account of International Women's Day was indeed very effective with Professor Gabriela Casalino, who presented on data analysis. Ma'am, your presentation about basics of fuzzy logic was very good. Fuzzy clustering was pictorially explained, which was very effective, ma'am. The data streaming, the algorithms were explained, and education data analysis with case study. Pretty interesting, actually. The data interpretation was explained very well. The digital health about bipolar disorder episode prediction, the model data analysis, and most importantly, need of the hour, suitable to the online platform, the cyber security. Since all of us are hanging around the online platforms, I think cyber security is need of the hour now. Thank you, ma'am. It was very informative, and as Parameshwari sir told, you answered all the question and answers, the question answer session. You handled it very well, and technically you excelled in that too. And looking forward to listen more from you, ma'am. Thank you. Thank you. Have a nice weekend.
Thank you.
Thank you, ma'am, for your valuable remarks. As we have come to the end of the webinar, I'd like to convey my deep regards and hearty thanks to the resource person of today's webinar, Dr. Gabriela Casalino, ma'am, for accepting our invitation. Thank you very much, ma'am. On behalf of IEEE Mysore subsection, I request you to accept this virtual memento as a token of gratitude.
Yeah, thank you, madam.
Okay, thank you.
Yeah, thank you.
Thank you
Thank
so
you
much.
for having invited me.
Yeah,
Thank you.
thank you, madam. Bye.
Bye-bye. Good night.
Bye.
Bye-bye. Hope to see you in person in India or somewhere else. Whenever
Yeah.
you want to come here in Italy, I will be happy to host you and to show you my region, my university.
Thank you. Thank you, madam. Thanks a lot.
Provided we are safe from pandemic, ma'am.
Yes, yes, we have to wait.
Yeah.
Bye to everybody.
Bye-bye.
Ciao.